Hi friends, this is Orgho from Pattern World. So in this tutorial, we'll explain you what is the complexity of this algorithm. So also we'll discuss what is the desired properties of the algorithm and what is asymptotic notations. At the end, we'll try to find out the time complexity of this algorithm. So let's begin. What is algorithm? The word algorithm may not seem relevant to you, but the truth is algorithm is all around you, governing everything from the technology that you use in your day-to-day life. There are algorithms. So it is a basically detailed step-by-step instruction set or formula for setting a problem or computing a task. So let's go back to your school days. Just think of the morning routine when you were in your school. When alarm rings occurs, you used to hit snooze button and wait until the alarm rings. Again repeat it for 2-3 times. Then finally turn off the alarm and get up, take a bath, get dressed, eat breakfast. At last, if it's a sunny day, you start walking towards school, or else you go to your school with your parents. Okay, so this is what the algorithm is. That means basically this is something we have written down in the English like words, so you can understand what is the algorithm. Anything that you have to follow, there are some steps that should be maintained in order to come to the particular desired set, that is algorithm. In computer world also, when we write down any programmer write down that in scratch and something like some blueprint of the program before actual coding. That is what the algorithm is. So coming to the properties of the algorithm, an algorithm should have two conditions. One is correctness and another one is the complexity. Correctness means the way to compute the correct or desired output for the given problem. Okay, and what is complexity? Complexity means there is two types of complexity. One is time complexity, another one is space complexity. Time complexity means the measuring how fast the algorithm is, that comes under the time complexity analysis, and measuring what amount of memory it will use, that will come under the space complexity analysis. Let's take an example. So basically, let's say there is a problem P. That's a problem. Let me write down here. There's a problem P, and programmer 1, programmer 2, and programmer 3 has written three algorithms A1, A2, and A3, which is basically for problem P. Both are giving the same output. Still, we will select some particular algorithm from A1, A2, and A3. Which algorithm shall we select? Now we will check which algorithm is taking less time and less space. Let's say algorithm A2 is taking less time and less space. So we will give vote to the algorithm A2 and select it for the program P and bind it with it. So basically, in each algorithm we have to think that it is taking less time and less space. We'll also discuss space complexity in some details. Let me go to the next slide. So as I said right now, what is space complexity? Space complexity of an algorithm is the total space that has been taken by the algorithm with respect to its input size. Let me explain it with the help of an example. So now go back to your initial days of C coding, when you used to ask to find out the summation of two numbers like this. So what we used to do, if we are asked to find out summation of two numbers, we used to take some integer variables a, b, and one is result, let's say like this, and then we will take the input a, b, and in result variable we will add these two numbers and print the result variables. So if we are working in a turbo C32-bit environment, we have taken 3 integers, and as integer is taking 2 bytes of memory, it will take 3 into 2 equal to 6 bytes of memory space. Suppose you have taken an unnecessary variable, let's say t, which you have not used in this program, but again you have taken it. So when it will compile, it will take total 8 bytes of memory space, but it should be done in 6 bytes of memory space only. So space complexity suggests that we should not take any extra unnecessary variables that is not required for this problem. Okay, so we will have to think as little memory as possible, we have to take that. Okay, fine. Now let me go to the next slide. We will try to understand the complexity function of an algorithm. We will understand it with the help of an example. So let me take a small pseudocode in order to explain it to you. So let's take it, any code. Okay, 1 minute. So let's take it. For I equal to 1, I less than equal to n, I plus plus, and within that one printf is there. Okay, let's say it's printf, it's printing something a. Okay, suppose you are asked to find out the total number of operations that has been done in this for loop. So what will we do? We'll first break this for loop in 3 parts. There is one initialization part, one condition checking part, and one increment decrement, that is increment here, increment part, and one is another instruction is there, which is the body part of the for loop. So as we are asked to find out the total number of operations that is required by this for loop, we have divided the entire scenario. Now let's try to understand for the first part 1, that is basically I equal to 1. So how many times this instruction will be executed? This will execute how many times? This will execute only one time only, because initialization will be done only in the beginning of the for loop. Then part 2, which is basically I less than equal to n. So this will execute how many times? N number of times? No, it will execute n plus 1 number of times. Why? Let's say n equal to 2. So when I equal to 1, it will basically check 1 is less than equal to 2 or not. Then it will be printing a and again increment it by 1. So it will check 2 is less than equal to 2 or not. It will again return true. Last time also it has returned true. And also after returning true, it will print the a. And then again it will be incremented by 1 and it will try to check if 3 is less than equal to 2 or not, which will return false. That will help the for loop to come out of this loop and execute the next lines of codes. Okay, so basically this will execute n number of times plus 1 number of times, n number of times for true part and 1 number of times for the false part. Okay, and how many times this I plus plus will be executed? This will simply executed n number of times, and printf part will also execute n number of times. So total we can say that if we add it, sum it up, so it is 3n plus 2 number of times. So total operation is 3n plus 2 operations we are performing here. We were asked to find out the number of operations required by this for loop. We can say the total number of operations is 3n plus 2. Now if one operation is taking 1 second of time to execute, so 3n plus 2 operation will take 3n plus 2 second of time. Fine, am I right? So now if the same thing you are asked to represent it in a graph, how will you represent that? Suppose this axis we are expressing input, and in this axis we are expressing the time growth, that is t. So if n equal to 10, it will take 3 into 10 plus 2, 32 seconds of time. If I increase n equal to 100, it will take 302 seconds of time. That means if we are increasing the input, time is also increasing. So let's say this graph is like quite somehow like this. So let's say it fn, this graph is fn, which is equal to basically 3n plus 2. That means if I increase the input, time will also increase. Okay, so can we say that this graph is basically expressing the behavior of this algorithm or the growth rate of this algorithm? So the behavior or the growth rate of this algorithm is simply the complexity function fn of this algorithm. So from this graph we can say that the algorithm will take more time when will increase the input size in 100 to 1000 to 1 billion. So it will take more time. So from this graph we can say, so this graph is basically the complexity function or fn. This is the complexity function of this algorithm. Hope you have understood this concept. Okay, so now let me go to the next slide. So now we'll explain what is the asymptotic notations. Just before some time we have explained what is the complexity function of an algorithm, just like where we had drawn a graph like this. This side is the input n, this side is the time growth t. Suppose there is an algorithm which is taking like this, expressing this behavior. So that means when I am increasing the input, it is also taking more time. And let's say this is algorithm A1's behavior. There is another algorithm which is behaving like this, like this. That means when I am increasing input, it was taking more time, but after a certain amount of time, it is taking less number of time even if I am increasing the input. Okay, let's say this is algorithm A2. So this algorithm A1's behavior, this is algorithm A2's behavior. So basically asymptotic notation will help us to understand the behavior of this algorithm. If I increase the input size, will it take more time, or if I increase the input time, so it will take less time. So all those answers we will get from the asymptotic notations. There are three asymptotic notation. Number one is big O notation, number two is omega, number three is theta notations. So we will try to understand all those three. Okay, let me go to my workspace. So now we'll first understand what is big O notation. Okay, so we'll here understand what is big O notation. We express it like this: capital O, represent is with capital O. So let me draw the graph again. This is the graph, this is the input size n, this is the time growth t, and this is some behavior of an algorithm, that you can say the growth rate of an algorithm fn. Fn is a function of n, where n is the input, which is let's say 3n plus 2 that we had discussed just right now. So as the input size is increasing, the time is also increasing, we can see from this graph. So when we keep on giving more input, so the time will increase like this. Okay, so if you are asked to find the worst case or the upper bound for this function fn, so how will we do? So we will find another function, say that is gn. We will find another function that is gn in such a way that it is greater than of fn after some input n equal to n0. Let's say gn is like this. After some input, it has become greater than fn. Let's say it is c of gn. So what I said, after some input, that is n equal to n0, after that, after this point, this function gn is greater than fn. So then we can say that from here we can say that, what we can say? We can say fn is less than equal to c of gn, where n greater than equal to n0. Here c and n are the real number and n0 is greater than equal to 1. Why n0 is greater than 1? n0 means basically input. There should be at least one input in order to check the algorithm. 0 input will simply say nothing. Okay, so if these conditions are satisfying, so then we can say that fn is basically order of gn. Okay, so in order to check this all these conditions should be satisfied. Okay, so let's take an example. Let's say fn equal to 3n plus 2 and fn equal to 3n plus 2 and gn equal to n. Now we have to find out two constants c and n0 such that fn is less than equal to g of n. So 3n plus 2 is less than equal to gn, and c of gn means n. So for some c which is greater than 0 and n0 greater than equal to 1, so we will substitute any value for c here. Let's say c equal to let's say 4. So then it will satisfy this condition, 3n plus 2 is greater than equal to 4n. Any value of c which is greater than 3 will satisfy this equation. So here if we take it to this side, it will come n is greater than equal to 2. We have found that n0, that is the input, and also c, and this condition is also satisfying. That means we can say that for these two functions fn and gn, we can say that fn equal to order of gn. That means gn is the upper bound for this function fn. Gn equal to n is the upper bound for this function fn, which is 3n plus 2. And as gn has become the upper bound for this fn, so gn equal to n square will also be the upper bound for this function. Also it will gn equal to nq will also become the upper bound for this function, because that graph will look like something n square like this, nq will look like this. So we don't have to think all those. You can just simply remember that when we will have to take the basically the least upper bound of all the upper bounds that are satisfying these conditions. Okay, so here we have understood the big O notation of an algorithm. Now let me go to the big omega notation. Okay, so let's start the big omega notation. Will help you to understand big omega notation. So we'll express it like this. Big omega is the representation symbol. Let's take the same graph, an example. So this is the input size n, this is the time t, this is some behavior of the algorithm. Let's say this is fn, which is, again we are taking the same example, 3n plus 2. So here we are basically asked to find out the lower bound for fn. Okay, so let's say there is another function gn after some amount of time where n equal to n0, it is behaving like this. This is c of gn. So then we can say that after some amount of time, which is basically this point is basically n, this is basically n0, n equal to n0, means this point is basically n0, this point. After n greater than n0, this c1 gn is lesser than fn. That means we can say that c of gn is less than equal to fn, where what are the all those conditions, where c and n are the real number and c greater than 0, n0 greater than equal to 1. Then if this is satisfying, we can say that fn is basically omega of gn. Okay, now let's try to take two let's take two example. So fn is 3n plus 2, let's say gn is n. Okay, so we are trying to check this condition, if it is satisfying or not, then we can say it is the omega of this. So 3n plus 2, this is the fn, is greater than equal to sum c and gn, that is basically n. Now try to substitute any value for c. So if I say c equal to 1, substitute c equal to 1, then it will become 3n plus 2 will greater than equal to n, where c, we have found this constant c equal to 1 and n will be greater than equal to 1. If I take this side, 2n greater than equal to 1, so n to 2, n greater than equal to 1. So this is satisfying. So we can say simply that for these two functions fn and gn, we can say that fn is basically omega of gn, which simply means that 3n plus 2 is basically lower bounded by n, is lower bounded by n. Okay, so this omega is representing the lower bound of any algorithm, lower bound. And last time we had explained BIGO, this will help you out to find the upper bound. So omega will explain the lower bound and BIGO explain the upper bound of any function. Hope you have understood this. Now we'll help you out to understand what is big theta notation. What is big theta? We represent it like this. So for the same graph, this is n, this is time t. Let's say this is the behavior of any algorithm fn, which is equal to basically 3n plus 2. So for this, basically I should find both upper bound and the lower bound of this fn by varying the constant. Okay, we'll check if fn is bounded by both the upper bound and the lower bound of this function. Let's say after some point n equal to n0, after some point n equal to n0, what's happening is that, let's say this is c1 of gn and this is c2 of gn. So after some point we can say that fn equal to theta of gn if c1 of gn is less than equal to fn is greater than equal to fn and which is less than equal to c2 of gn, means both upper bound and lower bound should be satisfied. Okay, then only we can say this is the fn is the theta of gn for all those constants c1 and c2 greater than 0 and n greater than equal to n0, where n0 greater than equal to 1. So let's take if it is satisfying or not. So let's take fn equal to 3n plus 2 and gn equal to n, and now we are trying to match if fn is less than equal to c of gn. So 3n plus 2 is less than equal to sum c into n. If we substitute the c with 4, then it will become 3n plus 2 is less than equal to 4n. So let's say it is c2. So we have found c2 equal to 4, where basically n0 will be greater than equal to 1. So this is the upper bound. So we have found the upper bound for this function is satisfying. So and in order to satisfy the lower bound, let's take what we have to satisfy. Fn is greater than equal to sum c into gn. Okay, so what is fn? Fn is basically 3n plus 2. It should be greater than equal to sum c into n. If we substitute c with 1, so it will become 3n plus 2 is greater than equal to 1 into n. That means n only. Okay, so here it is also satisfying. So it is also satisfying the lower bound of this fn. So then we can say that fn is really bounded by its upper bound and lower bound after sum n equal to n0. Okay, So we can say Fn is theta of Gn. Okay, so this is the theta notation. Okay, big theta. So hope you have understood this one. Now try to know what is its usefulness. So we have seen big O notation, then big omega notation and theta notation, but what is its practical significance? Basically, if you are giving the time of an algorithm in terms of big O, that simply means that it will not exceed this time in any case. That means it will basically represent the worst case of any algorithm. And if you represent the time in terms of omega, that means it is basically giving you the best case of the algorithm, and theta is basically giving you the average case of this algorithm. Okay, let's try to take an example, so it will help you out what is this best case, average case and worst case. Take an array. Let's say there are some elements in this array. Let's say that is 5, 7, 10, 15, 30, both are there, and you are asked to find 5 here. So we will do linear search here. So what is linear search? Basically we will start finding from the first element of this array and try to check if the element is present here or not. We will go one after another, not go to any other position. So we will try to check from the beginning and go one after another. If it is not found there, we will try to check here, then here, then here, then at the end. So when we are asked to find 5, we will find the 5 in the first location of this array, that is in the first iteration only we will find it. That means it is the best case that can ever happen to this algorithm. So we can say that best case in the omega of 1 notation, best case. And what is the worst case for this algorithm? So if you are asked to find 30, so you will start from here, and when you will not find that, you will come here and try to check if 7 is equal to 30 or not. So it is not that. So again you will come here, then here, then here, at last you will find this 30. So it will take order of n, that means n number of times to find this 30. So we can say that worst case of this algorithm is order of n. Okay, so or else if you are asked to find 300, which is not present in this list, still it will take order of n number of times only. That means it will try to search from the beginning, here, 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 no, it's not present. After searching n number of times, it will say it is not present. That means order of n, from this order of n we can say that this algorithm will not take more than this time. Okay, this is the worst case that can happen to this algorithm. And what is average case theta? There are some algorithm where best case and the worst case both are same. In that time we go for the average case of that. Okay, so maximum time we are basically not focusing with the average case and the best case of this algorithm. We have to give more time to find out the worst case, because this is what is important. Okay, hope you have understood this. So if there is any problem, you can post us, we will help it out. Okay, so in the next video we will explain you some more concepts. For the time being, if there is any query, you can post here. Thank you.